Yeah, Assalamualaikum and good afternoon to everyone. How are you? I hope you guys are healthy and can continue yeah, learning during this pandemic and you're blessed with good health. Okay, so today we plan to finish chapter 3 finally, alhamdulillah. And for the first part of our video, I'll finish the generation for the generation of wideband FM. So on Monday, we stopped at indirect FM generation using phase modulator, which is Armstrong method. And today, and for this first part, we'll continue with the how to generate wideband FM signal from our narrowband FM signals. Okay, so this is the block diagram of wideband FM generation. So the first part here, we have our narrowband FM modulator, which becomes the input to our wideband FM. So the narrowband FM modulator here can be indirect or direct. Doesn't matter. And because of the very small frequency deviation, which is not up to the requirements of commercial FM, you have to multiply, increase the frequency deviation. So we use frequency multiplier with factor n, where this frequency multiplier will not only multiplies our frequency deviation, but it will also multiplies our operating frequency and also modulation index. Okay, so here, if our operating frequency is omega C1 of the narrowband FM modulator, after frequency multiplier, it becomes n omega C1. And then only we will send the output from our frequency multiplier to mixer, and then to bandpass filter. And after that, we have our wideband FM voltage. Okay, let's look mathematically what happens. How can they be multiplied? Okay, so after frequency multiplier, okay, so this is our narrowband FM output. The instantaneous frequency is equal to omega C plus our phase deviation, first derivative of our VCT. And output of the frequency multiplier, here we use omega 2t, which is equal to n omega C1t. So it's equal to n omega C plus Vc dot t. So then it becomes omega C, which will become omega 2 plus n Vct dot. So our omega C2 is also equal to n omega C. So here we see how after multiplier, our operating frequency is multiplied by n. Okay. So next, in this slide, we want to show how the modulation index is multiplied by n. Okay, so our angle theta 2t is equal to the integration of our instantaneous frequency omega 2t, which is equal to omega c2t plus n Vct. Okay, this is from previous slide. Okay, so we know that the n Vct is also equal to n beta 1 sine omega mt, where our Vct is beta sine omega mt. So here our modulation index is also multiplied by n. So it becomes n beta 1, so it becomes beta 2 here, where beta 2 is equal to n beta 1. So from here, you can see how our modulation index is also increased by n times. And then the output equation after our frequency multiplier is EC cos theta 2t, where theta 2t is equal to omega C2 plus n phi ct. So we'll multiply, after multiplier, we send to mixer. At the mixer, we multiply our multiplied FM signal with FLO. So this is our multiplied signal times our FLO. So as usual, it will produce the upper and lower sidebands. So for the upper sideband is omega C2 plus omega L0 plus n phi ct. For the lower sidebands, omega C2 minus omega L0 plus n phi ct. And after that, we send it to band pass filter because we need to tune either at omega C2 plus omega L0 or omega C2 minus omega L0. So then the wideband FM equations is either the first or the second equations here. Okay, so the output wideband FM is either the one on top here, number 1, or number 2. So our band pass filter will be tuned to choose either one. And just to summarize what happens at this wideband FM process, if you compare with the original narrowband FM equation, which is equal to EC cos omega CT plus phi CT, the operating frequencies and also the phase deviation phi CT will be multiplied together with modulation index. So this is our original narrowband FM equations parameters. So you can see after multiplier, all these are multiplied by n except omega m, the information signal frequency. Here, omega m does not change. It will stay at its original value, omega m. And with mixer, our operating frequency will be changed, either plus or minus omega L0. So from omega C2, it's changed to omega C2 plus minus omega L0. Okay. Okay, let's go through this example on this block diagram. So this block diagram shows how we generate wideband FM using narrowband FM based on Armstrong phase modulator. So in here, we use 2 multipliers. If you notice, we have multipliers in front, and in front and behind this mixer. So our mixer is in between lah, N1 and N2. So output from our Armstrong phase modulator is, so the F is 500 kilohertz and the frequency deviation is around 15 hertz. Okay, so here I label Fi and delta Fi. So our FM station, we need to operate at 90.9 megahertz and maximum deviation at 75 kilohertz. So since the deviation from indirect narrowband FM is very small at 15 hertz, how do we increase the deviation? But the operating frequency that we want is 90.9 megahertz. If we use multiplier directly to increase the frequency deviation from 15 to 75 kilohertz, the factor is 5K, right? So 75K divided by 15 hertz, it's equal to 5K, right? And this 5K, if you multiply 5K with 15 hertz, we get 75 kilohertz. But if you multiply 500 kilohertz with 5K, we get 2.5 gigahertz which is very large compared to what we want. Okay, that's why we have this mixer to downgrade, to reduce our frequency, eh, so it becomes 90.9 megahertz. So we have to choose our FLO appropriately so that we can get the value that we want. Okay, so here after mixer, okay, first after the first multiplier here with factor N1, okay, our F then becomes N1 Fi and N1 delta Fi. So F is 81 megahertz and the phase deviation here increased to 2.5 kilohertz. So after the mixer, F becomes around 3 megahertz and the frequency deviation does not change. Yeah. So that's why the main purpose is to downgrade the frequency, but the or the frequency deviation is fixed. After the second multiplier with factor N2, okay, the output here is equal to N2 times N1 Fi minus FLO. And the delta FO is N2 N1 times delta Fi. So this is the equations at the outputs here. So we get our F at the desired frequency, 90.9 megahertz, and delta F at 75 kilohertz. Okay, so in order to solve this problem, you have to use all these equations and solve them. Okay, next is, let's go through one example that I have shared. I've shared this example before and on Monday. Okay, so let's solve this example. Okay, so in this example from final year exam session 2016-17 semester 1, okay, we are asked to design a wideband frequency modulator using Armstrong method that is equipped with a crystal oscillator that generates 200 kilohertz signal and modulation index equal to 0.2. Okay, and the system needs to transmit audio signals between 50 to 15 kilohertz. And the wideband FM transmitter supposed to transmit signal at 108 megahertz with deviation of 75 kilohertz. So these are the operating frequencies and the frequency deviation for our wideband FM transmitter. So you need to draw the wideband FM block diagram showing all the related parameters as well as carrier frequencies and deviation after each component. Okay, so you need to label all of them in your block diagram, and the chosen mixer frequency should be in the range between 20 to 25 megahertz. So we're given the range for our FLO or our mixer. So this will guide us on the suitable value for our mixer. And the multiplier factors N1 and N2 are integer between 2 to 10. Okay, so here you're given 2 multiplier factors. So we know that we need to use 2 multipliers. And this is the range of our multiplier factor. Okay, so let's see how we solve this problem. So normally a design question like this will contribute to quite high marks. So at least 5. So in this case it's 7. Okay, let's sketch our block diagram. So our solution. Okay, so we're going to use Armstrong. So you need to show in your narrowband FM. It's Armstrong. Okay, so this is our generating local oscillators to generate frequency at Armstrong modulator, and our VMT. So this is between 50 Hertz to 15 kilohertz. And over here, the F is at 200 kilohertz. Okay, so you're given beta of our Armstrong is equal to 0.2. Okay, so this is our narrowband FM part. And then we have our first multiplier, N1. Then we have our mixer. So we have two inputs to our mixer, FLO, another one. So this is for the mixer. And then another one, and two. And here is our wideband FM signal. Okay. So you need to label the F and delta F at point here, 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 and also over here. Okay, before that, okay, we need to have band pass filter. Okay, sorry for the drawing. It's difficult to control the pen. Our band pass filter, and then here is our N2 and V wideband FM. Okay, so then this is our output. Yeah, so our output should be at 108 megahertz, and delta F output is at 75 kilohertz. Okay, so the range of our FLO here is from 20 to 25 megahertz. So we can label here. So this is our input. Okay, Fi, delta Fi. Here you can put F1, delta F1 after FLO, F2, delta F2, then another one, F out, this delta F out. Okay. So we know that Fi here is 200 kilohertz. What is delta F? Okay, we're given beta 0.2 and FM, and we can take the highest frequency, F max, which is equal to 15 kilohertz. So our delta Fi then is equal to beta times FM, F max. So 0.2 times 15K is equal to 3 kilohertz. So we got Fi equal to 200 kilohertz and delta Fi 3 kilohertz. So you need to solve all the others, which is F1, what is F1, delta F1, and also F2, delta F2, and then F out, delta F out. need to also label our FLO N1 and 2. So these are the important parameters that we have to label on our block diagram, in our block diagram. Okay, so delta F3, you know that delta F3 is or delta F out, out is equal to N1 and 2 delta Fi. So 75 kilohertz is equal to N1 and 2 times 3 kilohertz. So our N1 and 2 should be 25. Okay, 25 divided by 3. So if you remember in the question, it says that N1 and N2 should be integer in between 2 to 10. Yeah. So obviously from here, our N1 and N2 should be equal to 5. Okay. So this is the only possible integer that fulfill our condition here. So we know N1 is equal to 5, then we can find our F1. So F1 is equal to N1, yeah, Fi, which is equal to 5 times 200 kilohertz. This one is 1 megahertz. And our delta F1 is equal to N1 delta Fi. So 5 times 3 kilohertz, which is equal to 15 kilohertz. So this is our F1 and delta F1 after the first multiplier. Okay. Let's look at the... So we have to still find the other parameters. Yeah, F2, delta F2, FLO. Okay. So let's solve the rest. Okay, so F2, yeah, over here should be equal to F1 plus minus our F mixer. And we know that our F3 is equal to N2F2. Okay, so basically we have all the values and equations we need to solve. Yeah. So F3 is 108 megahertz, which is equal to N2 times our F1 plus minus our F mix. Okay, N2 is equal to 5, F1 is 1 megahertz plus minus our F mixer. Okay, it's equal to 5 megahertz plus minus 5 times the frequency of mixer. So then we got our, and from this equation we got our F mixer equal to plus minus, okay, this 103 divided by 5 megahertz. So F mixer, remember it's between 20 to 25, so it should be If you solve this, you got 20.6 megahertz. Okay, so this is our mixer value. So from this mixer, we can get our F2. Then since F2 is equal to F1 plus minus, obviously here is plus our mixer. Then we got our F2 is equal to, so our F1 is 1 megahertz. So F2 is 21.6 megahertz. Okay. So, okay. So here, yeah, we got all our values that we need. Okay, just to list all of them. F1 is 1 megahertz. Delta F1 is 15 kilohertz. This one you have shown. And then F2 is 21.6 megahertz. Delta F2 is equal to 15 kilohertz. Over here, it's the same. Okay, after mixer, F3, which is also equal to, F3 is, over here is actually F out lah. F out, which is equal to 108. This is given, but you have to label in your block diagram. Delta F out is 75 kilohertz. Okay. And F mixer also you have to label 20.6 here. Mixer 20.6 megahertz. And our N1 is equal to 5, and 2 is also equal to 5. So these values, all of them you have to label in your solution. Okay. So actually it's not that difficult because the equations are all very simple. You just need to solve them one by one. Okay, so with this solution, I will stop for the first part of our wideband FM generation, and in the next part 2, we'll continue with a little bit summary before we enter the demodulation part. Okay, see you in the next part.